Here we are looking at the relationship between the focal length and the radius of curvature of a concave mirror, right? And in the next video, or in the same video, I'll also look at the same relationship between focus and the radius of curvature of a convex mirror also. So just to save time, I have already drawn the diagram. This is a concave mirror, as you can see. This is the inside surface. This is the reflecting surface, and we have an object placed over here. This is, say, the focus of the mirror, and this is this center of curvature. This is the pole of the mirror. Right? I'm assuming that you are well versed with these terms: the focus, focal length, center of curvature, and radius of curvature. As you know, PC, right? PC will be the radius of curvature, which is denoted by capital R. So PC is equal to R, radius of curvature, and PF is equal to the focal length F. Now, since this is a concave mirror, a ray of light which travels from this object, right, and is incident on this mirror, travels straight, something like this. So there is a ray of light which is incident on the mirror. This is the object, say AB. Let us call this point as D. So it's incident over here, and since it is parallel to the principal axis, it will reflect in such a way that it will pass through the focus. So this ray will go in this particular way. It will reflect in such a way that it passes through the focus. So this is the direction in which the ray goes. Now, if I draw a line which joins center of curvature to this point, so let me draw a line over here. Of course, this is not a ray. I'm just drawing an imaginary line which connects the center of curvature to this point of incidence. Now, this mirror is a part of a sphere. So the line which joins the center of curvature to this is normal over here, is perpendicular over here. So this serves as the normal. Therefore, CD is the normal, because CD will be perpendicular over here, meaning if I draw a tangent over here, this angle will turn out to be 90 degree, right? And that is the feature of any sphere, right? If you have a sphere, right, and a line which joins the center of the sphere to any point on the surface is perpendicular over here. So since this is a part of a sphere, the line joining the center of curvature is perpendicular. Therefore, CD serves as the normal. So if CD is the normal, then this angle becomes the angle of incidence. This ray is traveling in this direction, is incident at this point. This is the normal. This is the angle of incidence, and this is the angle of reflection. Now I'll just use a little bit of geometry over here, right? If this is angle I, right, then this will also turn out to be angle I, and that is because these are alternate angles. Just for sake of explanation, if I draw AD over here and CP, these two are parallel lines, and this DC, this is DC. So you can see these two are parallel lines, and this acts like a transversal. So if this is angle I, this is also angle I, because they are alternate angles. So this is also angle I. Now, if I focus my attention on triangle DCF, in this triangle I am seeing I is equal to R. These are the two angles, I and R. So I have found out that this is I and this is equal to I. So these two angles are equal, because angle of incidence is always equal to angle of reflection in case of reflection process. So I is equal to R. So these two angles are equal. Therefore, the sides opposite to these two angles also will be equal. The side opposite to I is FD, and the side opposite to R is CF. So these two sides will also be equal because the two angles are equal. Now, if I look at FD, right, this side, FD, I can consider FD is equal to FP, assuming very small aperture of the mirror. I am assuming this mirror is extremely small. The aperture is very, very small. Therefore, FD is equal to FP. Let me explain. We are assuming that this mirror, even though it is shown over here, has got a very small aperture. It's extremely, extremely small. So therefore, FP and FD, both these lines will be nearly equal. The difference between them will be very, very small. Let us say we have a right angle triangle. So if this is the right angle triangle, if I draw this line, if this angle is large, Right? If this, or let us say this height is very, very large, then there is a substantial difference between this length and this length. But if this length becomes very, very small, say for example I decrease this, or let us say the length is now only this much, then this line becomes equal to this, and you can see the difference between them will decrease. And if I take it very, very close, means if this line is very, very small, that means it is something like the aperture of the mirror. If it is very small, the difference between these two lines is very small. The difference in the length is very, very small. So I can practically say that this line is equal to this line. And that's what we have done. We have taken FD is equal to FP. FD is equal to FP. Therefore, in this equation, FD I can write as FP. Therefore, FP is equal to CF. Therefore, FD, FP, this is FP, this is FP, is equal to CF. Therefore, if these two lines are equal, then I can write down PF or FP is equal to half of PC, half of PC. Now, what is PF? PF is focal length F, and what is PC? PC is radius of curvature R. Therefore, R is equal to 2F. And this is what we observe in case of mirrors, that the focal length is half the radius of curvature. We can do similar thing with a concave mirror also, and the similar exercises we can do with the concave mirror. So let's say we have a concave mirror. This is the focus. This is the center of curvature. Let me let us say this is the incident ray from the object coming over here and meeting at this particular point F. This will get reflected in such a way that the point appears to come from focus. So this will get reflected in this direction, and it will appear to come from the focus. I can join this, make it over here. So if let us say this is A, B, this is pole. Let us say this is the point D over here, and it goes in this direction. As we did in the previous case, let us draw imaginary line from the center of curvature passing through this point. So I can show this line. And as we discussed just a few minutes back, the line joining the center of curvature to the mirror is normal. So if this is incident ray, this becomes angle of incidence, this becomes angle of reflection. Now we can very clearly see over here this line is passing from C, and this is I. So if this is I, this angle also becomes I, because we have a common line, and these two lines AD and BC are parallel to each other. So this angle is also equal to I. If you look at this angle will be equal to R, because R and this R, they're vertically opposite angles. So now if I focus my attention on triangle DFC and do a similar exercise as I did with concave mirror, I is equal to R, because that is the case with reflection of light. So what I will get is CF, the side which is opposite to R, CF is equal to the side which is opposite to I, which is FD. And again, as we discussed in the previous video, I can consider FD is equal to FP, assuming very, very small aperture. FD is equal to FP. The CF is equal to FP. So therefore, F is the midpoint of this particular, FC is equal to FP. Therefore, I can write down that PF or FP is equal to half of PC. And therefore, again, F is equal to half of PC is the radius of curvature R, and therefore I get F is equal to half of R is equal to F. Thus, we can show that in both the types of spherical mirrors, convex or concave, the radius of curvature is twice the focal length of the mirror. Thank you.